Hello everybody, this is Gabe and we're going to be continuing our talks about operating systems. Today we're going to talk about an abstraction for execution, which many of you are already familiar with, called processes. So what we've talked about leading up to now has largely focused around system structure. So system structure is, again, how different pieces of software on the system are isolated from each other. And if things are isolated, then if they need to communicate in some way, how do they do so? We talked about monolithic operating systems like Linux, OS X, Windows as having a very specific form of system structure where much of the logic that you would require in an operating system is in the kernel. So the structure that they provide then, the isolation that they provide is relatively minimal and is meant to only essentially isolate applications from each other and to isolate the kernel from applications as well using dual mode protection. Now the core abstraction for this is the process. The whole idea is effectively that to isolate these applications, we isolate them in processes. So what is a process? It is just an abstraction that the operating system provides for CPU and memory. So you have to start with what the hardware gives you, right? The hardware gives you a range of physical memory that you have literally on your board. If you buy a machine with 8 gigs of memory, then you essentially have an array of 8 gigs, right? And then the hardware provides you a sequential execution, the idea that you execute one instruction after the other, and interrupts, of course, to be able to communicate with device drivers and other things, as we'll learn today. The operating system's job is effectively to abstract this relatively mediocre set of capabilities and provide the ability to have multiple sequential executions, or as we call it, multiple flows of sequential execution that allows us to essentially execute different applications. And then each application should actually have what it thinks is its own memory space, essentially memory that it can access independent of any other process. And these should provide the foundation for protection between these applications, which we've learned is the foundation for security and fault isolation, or for system reliability. So what does a process look like? Let's kind of look at a life cycle very quickly. So at the top, you kind of see this sequence where you might start out with some source code and things like C files, Java files, whatever. In C, you often compile that to object files, the .o files. These are binaries, but they can't necessarily be run yet because they need to be combined with other objects first. So you combine them together with a linker into some sort of a binary, and we call that binary a program. The program exists on the file system and is loaded into memory using a loader, which loads the sections of that program into memory. And then the operating system is essentially pointed to it and said, start executing with the instruction pointer at the _start address, which we already saw in class. So processes are the latter stages here when the operating actually starts when the operating system starts executing the application, the process. So to make this very clear, an executable program is the type of thing that you see in LS. It is a program. It exists on the file system. It's not actually executing, right? It's a passive collection of code and data. It's kept in a file. A process, on the other hand, is an active entity that is executing on the CPU using resources and actually has active code, right? And you can see the processes that are executing in the system by using the ps command. So a process includes the registers for that process. So when we talk about a flow of execution, we talk essentially about the registers that track where we're executing and what the state of that execution is within a process. We have an execution stack, so we've talked about a lot. We have a heap for dynamic memory allocation, and we have global data and code segments. So this is effectively what a process is, and we've actually already seen processes to some degree. I'm going to start out by looking at a process that just has this code in it. So we just have a main, we have a global variable, and then we're printing out some stuff. Let's look at it in nicely formatted style first, and then we'll come back to this. So we see on the right the same program. We're malloking some code. We're malloking some memory. We're saving it in the variable s. Then we're printing out the address of s. Then we're printing out what s holds, keeping in mind it is a pointer, so it holds a pointer to some memory. Printing out the address of the global variable that we saw before, and then actually printing out the address of main. So we're essentially printing out a lot of different things here. And on the left, what you see is a pretty accurate representation of what a process looks like in memory. We'll call this the virtual address space of a process because it thinks all of memory on the system is its, starting from address 0 up to the maximum address here. But in reality, that's a abstraction provided by the operating system. So when we look at the address of s, we know that s is a local variable within this function, so that should be in the stack. So the address of s is on the stack, so we see the arrow from that stack variable pointing up to the stack. And if you look at the address of the stack, it's at BC8, 7, etc. It's at a relatively high address compared to the other addresses. When we look at the value that s contains, it's a pointer, so it contains a pointer to within the heap. And we can see that malloc is much lower than the stack in addresses, the address of malloc, but not near 0, right? When we print out the global variable, we see that that's even lower in the address space, 004C. And then when we print out the main, we see that it is at 000B. So we get lower and lower addresses, and that's why we use this kind of visual representation for that. And you can see the different pieces of the code annotated next to the place in the process that they exist. The text segment is really code. We call it text for historical reasons. The data segment includes the read-only and read-writable global data. The heap is malloc and free managed dynamic memory. And then there's a massive hole in the address space where essentially there is no actual memory. Attempting to access an address in those locations will result in a fault. A lot of times when you see segmentation faults, it could be because of this. And then the stack is at the high address. Let's go back to the actual code. So you can see this is the same thing. We have our variable s, and you can see that we're kind of printing out the address of s here, a reminder that's in the stack, right? Now, if we were to try to actually compile this program, we might run something like this. Note, if you want to follow along, I'm using a couple of flags here because I don't want position-independent code or a position-independent executable, just to make what it prints out as addresses a little bit clearer. You can look into those if you're interested, but you don't need to. Now, when we run the program, we can see that indeed the stack is at a very, very large address. Malloc is at a kind of not anywhere near that large, but at a higher address than the rest. And then we look at the global variable where main is. We see that those are at relatively low addresses. And in this case, I printed out the process identifier for this. What I want to do is look at the program for a.out with objdump relatively quickly, just so that you can see what it looks like, because we have used objdump before in the class, and I want to show you some of the other features of it. So objdump allows us to not just look at the assembly for this, but also a lot of additional information. What I want to draw your attention to here is this section specification. The sections are part of the way that we hold this format for data called an ELF object, ELF. And what we see is enumerated here a whole bunch of sections, and the most important ones that I want to point you to are the text segment, the read-only data segment, and following up from that, things like the data segment, etc. So let's look at what these actually are. I want to point you to the fact that the text segment, which again is the code, is, as objdump says, contains data that should be loaded into the virtual address space at this address. So let's remember that 590 there, right? If we look at where we actually printed out where main is, it's 400,590, right? Was where the segment was. This is just slightly offset above where the segment is, right? 400,590, that's where our code essentially starts, and we can see this is 400,677, so a little bit offset from where the code actually starts in the actual virtual address space. So we can see that objdump actually tells us a lot of information about our program and how it's laid out, and that program translates into how the program is loaded into memory when it starts to become a process. Because a.out is running here, it is actually the executing process corresponding to that program, right? Now, the next thing that I want to look at is the dynamic parts of that process, right? So objdump lets us look into a program. Let's look at the dynamic parts of the process. I know that the process identifier is 16845, and what I've done here is I've gone into my root file system, and within that, the proc file system, and then into a subdirectory that corresponds to the same number as the actual process ID for that process that I'm running. And what you see in here is a whole bunch of different files. All of these files actually describe different aspects of that dynamically executing program. They define so much context about that program that GDB actually uses all of this data to be able to be a debugger, to be able to look into the context of your program. So if you ever wonder how GDB is implemented, all that it's doing is really interpreting all of this proc data and then using a few little syscall tricks around ptrace. So what I want to draw your attention to start is this maps file. Okay, so maps is all of the memory mappings, all of the memory that exists within the virtual address space for this process, right? So this lets us look into the dynamic aspects of a process. And again, what you see here is a lot of stuff that has different addresses within the virtual address space. Now you see there's a slightly different specification for what these look like. And what I again want to do is compare these to the output that we got from our program that again was just printing out all of these different variables, right? So we know what this all looks like. Let's now compare it to this. So first, I want to draw your attention to the fact that because we are a process and we're executing, we now need a stack. And we can see that the stack is at a very high address range within the virtual address space. So 7FFCCA and then some other stuff. So let's look here. When we print out the stack address, we can see it's at 7FFCCA and then some other stuff. So we can actually see that we are now in this maps file looking at the actual virtual address space of the process as it's executing. And this is where the stack is at, which is pretty cool. I want to draw your attention next to the heap. We can see, I told you that the heap is where malloc actually allocates memory, and we can see that's at 16DD in terms of addresses. And if we look at where malloc has allocated, it's at 16DD and then at some offset into there, right? So we can see that actually malloc was called and it did allocate some memory for us, and it's within the heap here. And finally, if we look at this range of memory here between 4 and then all zeros and 401, we can see that that's actually where our actual code is. And I know that that's also where the code is because this tells us the permissions that we have for accessing that. And we can see that we can read the data there and we can execute the data there. That means it must be code, right? That's in contrast to the read-only data, that's constant global data that is only readable. And then we have read-writable data that is global within our program. So if we look at this, it's 601 to 602. And if we look at where our global data is, it's 601, between 601 and 602. So you can see that we have a lot of facilities in Linux, both in Obstemp to look at the program that is the file system entity, and then when we load that program into a process in the operating system, we have means to actually introspect into its virtual address space. And because there are so many files within the proc file system, there are many, many other things that you can do. So in general, what processes are then is just this ability for the operating system to use some mechanism in the hardware that we'll talk about later to provide this notion of virtual address space. And we saw that Linux goes a step further and provides us these kind of introspection facilities like the proc file system to implement debuggers and whatnot. Each of these virtual address spaces that every process runs in is obviously a lie. You can't have all of the memory from address 0 all the way up to 07 blah 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 blah, really, really high addresses for the stack. There actually isn't that much physical memory in the system, so it's absolutely a lie. So virtual address spaces are a lie, they're an abstraction, and they're used to provide protection between processes. So we just want to make sure as an operating system that different pieces of real memory, of physical memory, are mapped into those virtual address spaces for different processes. As long as there's different pieces of real memory mapped into these virtual addresses, then different virtual address spaces cannot access each other's memory, therefore we have isolation. Remember, isolation in many ways is the opposite of sharing. I've already lied to you a little bit, and I want to kind of work on that lie a little bit, right? So we saw in when we were looking into all of this that the code did not start at address 0. It started at 40 something, right? So why does the code not start at 0? As you can see here, I've actually drawn kind of an empty region in the virtual address space, which we see within that maps file for the process. There's a hole between 0 and n, 4x0, 0x4 in the Linux systems between 0 and n here. So the question is, why do you think there's a hole here? It's really not obvious. Penny's very excited to answer. She knows the answer to this one. She's a smart pup. Go ahead and pause, think about it. Okay, so the reason that there's a hole of inaccessible memory within every virtual address space here at address 0 is actually because of null. Null is equivalent to 0. So when we think of the null pointer, all that actually is the value 0. So when we dereference the null pointer, when we dereference 0, what we want is we want to receive a fault, right? So how do we receive a fault or some sort of exception if we actually dereference the null pointer? Well, we make sure that there's a region of inaccessible memory starting at 0. Now, it's not enough to only have the address 0 be inaccessible. You also have to have a region of memory that's inaccessible, because what if you have a pointer that points to an array, and then you want to offset into that array? When you dereference the actual pointer for the offset you're looking at, it will not be at address 0. But if your array was actually null, you would start referencing up from null at some other address. So we just want to make sure that any of those addresses that you might reference from a null pointer, be they in an array or a struct, will be inaccessible within this region. Okay. The second place where I've lied to you a little bit is with respect to the kernel. And the big question here is, where is the kernel within this model of a virtual address space? When we draw the addresses going from 0 up to some max, where is the kernel? Is it in a separate virtual address space? But we always talked about the kernel memory being relative to some dual mode protection, so it seems like that's important somewhere. So what kind of hardware support is provided for this, and where is the kernel for all of that, right? Now, it's important to understand why the kernel exists in this type of scenario, right? We've talked about the kernel managing all of the system's resources. Well, virtual address spaces are an abstraction provided for processes, and they are provided by the kernel. It's actually essential that the kernel is the thing providing these virtual address spaces and controlling what memory is valid within those address spaces and not, right? So you should ask yourself a question, why? Why is it important for the kernel to know that and to be the one controlling these virtual address spaces? Go ahead and think about it for a second, pause, come back. So the reason that the kernel really has to be the one managing these virtual address spaces is simply because if a process was able to manage its own virtual address space, then it could map any memory on the system into itself, including memory for the kernel. So instead of expanding the heap up, as the arrow shows on the picture, maybe the process decides to map part of the kernel into itself. And then it could corrupt the kernel because now it has access to that memory, right? It could also access other processes' virtual address spaces, right? So this is inherently just kind of an unsafe thing to be able to do. The kernel needs to provide safety between different virtual address spaces. Therefore, the kernel must manage the virtual address spaces in the system. Furthermore, to switch between virtual address spaces, it actually is a sensitive instruction. So the kernel must be involved when we're actually switching between virtual address spaces. But that leads to the question, how do we actually switch between virtual address spaces, right? So there has to essentially be, the logic for that has to be in the kernel, and essentially it has to be in some sort of a system call path. So when a process wants to wait for I/O, wait for an interrupt from some I/O device, or when it just wants to switch to another process, it better make a system call. There must be a system call for being able to do that. But the question is, I want to go back to the original question, where is the kernel within this system, right? Within a virtual address space, where lies the kernel? So what I've drawn here is a more accurate representation of what on a 32-bit system operating system virtual address space looks like. And you see at the top here that the kernel is mapped into the top gigabyte of that virtual address space. Now, I say gigabyte here because a virtual address space on a 32-bit system has to be 4 gigabytes typically. Because if you look at how many addresses, what values can be expressed within a 32-bit word, it's 2 to the 32. Right? And it just so happens to be that 2 to the 32 is about 4 gigabytes. So around about the upper gigabyte of a virtual address space is devoted to the kernel, and the lower 3 gigabytes is devoted to processes. So this leaves a big question as to how this could be safe. Right? If the kernel is within the virtual address space of every process, what protects the kernel from each of those processes, right? It also raises the question why the kernel isn't just in a separate address space on its own, right? So how does all of this work? Think of these two questions, why there's no separate address space holding the kernel, and why the kernel is protected even though it's in the same virtual address space as a user-level process's code. Think about it for a second, then we'll come back to it. Okay. The high-level idea here is effectively that we need to look back at how system calls work. You'll remember that for a system call, a special instruction is executed, either an int or a sysinter on a 32-bit x86 system. And this instruction switches to mode 0, to kernel mode, and starts executing at a certain address with a certain stack pre-configured by the kernel, right? So that's it. There's nothing else that a system call does. So we can't have the kernel in a separate virtual address space simply because if we want to make a system call, there's no part of a system call that switches address spaces, right? So the kernel has to be in the same address space because system calls, interrupts, and exceptions don't switch between address spaces, yet they need to execute the kernel, right? So then the question is, how's the kernel protected from the user level parts of the virtual address space? And that just comes back down to the dual mode execution properties that we previously talked about. Now it might make a little bit more sense when I say that the kernel memory is marked as being kernel memory, and the user memory is marked as being user level memory. And while you're executing in user mode, you simply are disallowed by the processor to access memory that has been marked as kernel mode memory. So that will trigger an exception, which the kernel will then process and say, hey, wait, you're trying to access my memory. You're not allowed to do that. And you'll get a seg fault or a general protection fault. The really weird thing is effectively that because every process has the kernel mapped into it in the upper gigabyte of its virtual address space, when we switch between address spaces, the kernel is present identically in every single virtual address space. So that kernel up layer looks exactly the same no matter which virtual address space you're in. Despite the fact, of course, that every virtual address space has quite different context for every single process for all of the user level stuff. What that means is that the kernel can switch between virtual address spaces using its sensitive instruction to do so, and just continue executing kernel's code after that, simply because before switching, it's executing in the kernel. After switching, it's still executing in the same kernel code, even though it's in a different virtual address space. So I want to summarize where we're at so far. We looked at objdump to look at the sections of a program on disk, and we saw that those correspond to, when we execute the program, some of the addresses that we saw. So objdump has a lot of information in it that tells us where the code should be loaded, etc., where the data should be loaded, and all of that. So then when we run the program, it is loaded and we execute it, and we see indeed that some of those addresses correspond to each other. Then we saw that the proc file system, the process file system, for a specific process identifier includes a maps file, which actually lets us look at a dynamically executing program, right? Sorry, a dynamically executing process. And generally, we saw that a process is a high-level abstraction for execution in Unix that includes both a virtual address space, memory abstraction, and a flow of control, which we'll learn to find is what we call a thread. So the question is, how do you implement this, right? So that's kind of the abstraction. Now, how do we implement it? First, we have to think about what data structure should represent a process, and we typically call this something like the process control block, or in xv6 struct proc. So this is a data structure like any other struct that we define in C that the kernel defines, and there's one per process, and essentially it contains all of the data structures necessary for tracking the virtual address space, for tracking the register contents, and all of that stuff for a given process, right? So it includes the CPU registers, a state that process is in, any memory management information, where the virtual address space mappings are, etc. Things like CPU accounting information, how long this process is executed, and file system information for instance, things like how many open files it has. And we can actually see on xv6, on xv6, this is just a real structure. There's nothing special here, right? And I'm going to point out some of the things that I talked about. This pagedir variable is the page directory, the page table, which we'll learn about later. That includes all of the data structures that describe the virtual address space of the process. There's the size variable, which describes essentially the top of the heap within the process. There's a variable that points to where the kernel stack is for this process in the kernel. There's a variable tracking the state of the process identifier, and the trap frame and context are two variables that track, in some sense, the registers of that process. So this is just a C structure like any other structure that we define. The kernel is not special here. We implement processes using normal structures. The states that a process goes through as it executes are important to understand. So when you first try to execute a process on the shell or some other way, as we'll see by calling exec, or by calling fork and then exec, it starts out new and is admitted into the system when you execute that call. At that point, it goes into what is often called a ready state. Now, that ready state is essentially saying that it's ready to execute, but it's actually not running on the CPU at this point in time. Effectively, what we're doing is we're making many different processes run on the same CPU at the same time, which means only one of them can actually be running. It is in the running state on the right. The rest of the processes are in the ready state. So we're in the ready state until the operating system decides that we should execute. And what that's called is scheduler dispatch. We'll find that there's a scheduler in the system that dispatches the thread and starts executing it. When we're running, what might stop us running, right? We're executing on the system. What if we want to wait? We make some sort of I/O request and we want to wait for a we want to wait, right? We want to wait for that interrupt to happen in the future to wake us up. Well, in that case, we would go down into the waiting state. So we wait for some I/O event, right? And then when we're waiting, at some later point in time, that I/O event might happen. The interrupt might trigger that corresponds to the data that we requested. In that case, we go from the waiting state to the ready state. Additionally, if we're in a running state, what if an interrupt happens for another process that had previously asked for I/O? Well, in that case, the interrupt might transition us to the ready state because the operating system decided that instead of continuing running us, it wants to wake up and run that other thread that was in the waiting state and is now moving up into the ready and then the running state. And then when a process exits or when it faults, it triggers an exception, it might exit and go into a terminated state, right? So it's important to kind of understand the implications of this. If only one of the processes is in the running state at any point in time, that means that its registers are actually loaded in the system and it's executing. What state are the other processes in, right? Think about it. Yeah, they must be either in a waiting or ready state, right? Can you think of any additional reasons why a process might go from running to waiting? So there's waiting for I/O. Anything else? What if it didn't want to wait for I/O? What if it just wanted to block for some amount of time? What if it wanted to wait for talking, for communication with another process? There are many, many different reasons why it might wait. So, actually, sorry, let me go here. I told you that this state within xv6 tracks the state of the process, and it corresponds to essentially one of the states that we just looked at. It names these things different. Instead of the waiting sleep, there's the sleeping state. Instead of the ready state, there's the runnable state. This is runnable, but not running. the process that is loaded on the CPU and running, its register contents are active, is in the running state. And the code within the system encodes the transitions between each of these states. And for this process, it is always in exactly one of those states. Now, as we cycle between these states, we kind of need to track track what I/O processes are waiting on. We need to track all of the ready processes that are trying to become running. And we typically do these with some sort of abstract queue. They might be a priority queue, they might be a more intelligent queue than that, but in essence, we just want to kind of keep all of the processes in some form of a queue, right? So what are the queues that we have in the system? We have the processor job queue, and this includes all of the processes in the system, right? This is really just tracking every process in the system. If you wanted to halt the system, it would go through all of the processes here and say, all right, I need you all to terminate, right? We have a scheduling run queue. The run queue tracks all of the processes that are in the ready state, trying to go into the running state. So this is all of the processes that want to execute but are not currently, right? They're waiting to execute, and there is something on the system called the scheduler, which chooses the next process to run at any point in time. So it chooses from amongst the ready processes which one should go into the running state, which one we should actually execute now. Then there are device queues. So when we actually make a request to a device driver which knows how to talk to the I/O device, let's say we want to wait for a packet, right? That's our request. Well, we need to go into some sort of a queue that tracks that we are waiting for data from that device, so that when the interrupt comes in, that the data has been DMA'd into memory, we know which process was waiting for that data. So we typically have a device queue per process that tracks all of those processes waiting for those I/O events, waiting for the interrupts. There is typically one queue per device, but there might be multiple if the device is more complicated. And as processes effectively go through this state machine, from ready to running, they go from the scheduler run queue into the running state. When they go from the running state into the waiting state, they're effectively going on to a device wait queue or a device queue. And if we look at that graphically, we see this, that we're in the ready queue, the scheduler run queue when we actually want to execute. Then one process goes into the running state, its registers are loaded onto the CPU and it starts executing. And then that process might make an I/O request, which might in-queue it in the I/O queue, put it in the waiting state so it's no longer executing, and it essentially waits for an interrupt later on from the I/O. At that point, the scheduler needs to choose the next process to run from the ready queue because the one it was previously running no longer wants to use the CPU, right? So process scheduling is this notion of deciding which process to run at any given point in time. And there are a lot of kind of naive ways that you might think of this that I think are relatively intuitive. So these are things like process priority. So if I have a whole bunch of processes that want to execute at any point in time, I might have some that are higher priority than others. So I'll always prioritize those over the other ones. So that's kind of an intuitive reason that you might do this. But also we'll see that every process has kind of a time slice that we want them to execute for. A scheduler's job is not just to prioritize properly, but it's also often to maintain some notion of fairness, which is to say if one process wants to use a CPU and it's given some amount of CPU time, and another process that wants to use a CPU should be given roughly a comparable amount of time if they have the same priority. Right? So time slices is an intuition about that. We might want a process to run for a time slice and then switch over to another process, right? We do think about processes in a few general terms or nice generalizations for how processes behave. And we like to think of these as falling into two categories, CPU-bound and I/O-bound. CPU-bound processes are effectively those that spend most of their time on the CPU, not necessarily waiting for I/O. right? So scientific computations that are, computing pi, doing climate modeling, that type of thing, these are by default CPU bound, right? If you're mining for Bitcoins, these are CPU bound or maybe GPU bound. Then there are I/O bound processes, and those are effectively asleep most of the time. They're in the waiting state most of the time on device queues. And they typically wake up, process the data that they woke up to receive, and then go back to sleep waiting for the next batch of data. And you can imagine the X server on Linux, which handles keyboard input and output, mouse input and output, and works with your screen to display everything that you see. It might go to sleep waiting for keyboard or mouse input, and then wake up when you hit a key. It'll do a short amount of processing, make the key appear on screen, and then go back to sleep waiting for the next time you hit the keyboard. So this is a intuition about an I/O bound process. Web servers, for instance, are relatively I/O bound, right? So they execute on a server. They're waiting for network communication most of the time. They do some computation when they get a packet, and then they wait for more I/O bound computation. Now, the CPU generally prioritizes I/O bound processes because you generally want to essentially say, well, if you woke up for some I/O that just happened, maybe you should process that I/O immediately. When we talk about scheduling in a few lectures, we'll dive into this a lot more. So a general question is, what keeps a single CPU-bound process, perhaps even just executing an infinite loop, from monopolizing the CPU and not letting any other process ever run? I kind of mentioned this notion of a time slice, that we want to maintain fairness, and that's fair, that's what we want to do. But what is the mechanism that allows us to stop an infinite loop from executing on the system? I'll let you think about that for a second. Timer interrupts are the answer. The notion is effectively that there is a small little I/O or a small little device on every CPU that the operating system can program to cause an interrupt to happen either periodically, something like 100 times a second, 1,000 times a second, or it can tell it to just fire once at some offset into the future, at some time into the future. So the timer interrupts are effectively just a small little device that we can use to keep track of time. So timer interrupts effectively are there to provide fairness within the system, because if we have an an infinite loop executing process, a time interrupt will fire at, let's say, 10 milliseconds into the future if the timer interrupts fire 100 times a second. And the scheduler can at that point say, ooh, maybe I should stop executing this infinite loop process and execute another process to maintain time slices, to maintain fairness, right? The timer interrupts also are the main and only way for kernels to effectively keep time. So when you see the time displayed on your screen, that is effectively your operating system looking at the timer interrupt ticking 100 times a second and updating that clock based on that. I'm lying a little bit. They're like network time servers on the internet, but this is how operating systems maintain fine-grained time. So they allow the operating system to keep track of wall time and wall clock time, and they also allow the operating system to keep track of how long different processes have executed and decide if it wants to switch between them at any point in time. A process's time slice is typically a multiple of a timer interrupt in arrival time. So if timers happen 100 times a second every 10 milliseconds, then a process's time slice, how long we run it before we switch to the next process, would be a multiple of that. Now, one of the scheduler's most important jobs is essentially just to say, we have n CPUs on the system. I haven't mentioned this so far, but I want to mention it now. If we have n CPUs on the system, we can be executing n processes at the same time, one per core, because every core is a parallel set of registers that can be loaded. So we can run n processes at the same time on n CPUs, which is why they're faster, because we can do many things at once. But in many systems, the number of processes M is much, much larger than N, which you see in the title here, right? So the scheduler's job then is really to decide at any point in time which process to run given this, right? And the scheduler uses a mechanism for switching between processes called a context switch, or called a scheduler dispatch. And this is effectively logic, usually written in assembly, to save the registers of the previously executing process and load the registers of the one that we're trying to context switch to or dispatch to. And it will take the previous or the current process that's running on the system, save its registers and move it from the ready to the running state, and it will load in the registers of the next process we want to run and move it from the ready state to the running state. Now, it's important to understand that this context switch time, the amount of time that we're scheduling and switching between the processes, is all overhead. So we really want to minimize this because that is CPU cycles we're spending on something that is not productively executing applications, right? So the big question is, and I already answered this a little bit, but think about it and make sure that you understand it. What is involved in a context switch? What do we actually need to do when we context switch between two processes? What needs to be saved and restored? I'll let you think about it for a second. It's really all of the registers, right? We really need to save and restore all of the registers. I'm not going to go into it now, but it also means that we need to switch between the virtual address spaces, right? So we are activating the next process's virtual address space and deactivating the current register's virtual address space. So what this looks like a little bit more pictorially is that we see on the left P0, process 0 executing, process P1 executing on the right, and the blue colored arrows is actual execution of the process. So we see P0 executing at the start of time. Time proceeds downwards, and we get some sort of an interrupt or system call, let's say a timer interrupt in this case, and that activates the scheduler. The scheduler says, ooh, I want to stop executing P0 and start executing P1. I want to do a context switch from P0 to P1. So it saves the register state of P0 into its process control block, its struct proc. It reloads the register state from PCB1, the struct proc of process 1, into the CPU and starts executing it. So that entire context switch time here is denoted as idle. I just kind of think of it as, kind of wasted time overhead, right? And then P1 starts executing. After we've restored all of its registers, it has nothing to do but to register. So at that point, P0 is in the waiting state. It's not doing anything. And at some point, we might switch back to P1 from P0, which you see kind of in the lower transition. Now, I want to go into something relatively complicated, but I find that to understand what a context switch is, you really, really need to understand the mechanics. Otherwise, it really feels like magic. So what we're going to do is we're going to look at switch.s on xv6. Switch.x is an assembly file. .s is a assembly file. And this is the context switch code for xv6. You see at the very top something where it kind of specifies if this were a C function, what its prototype would be. So you see that it kind of takes what they call a struct context for the old process, and we're going to take save all of the current registers on the CPU into that context. That is the registers. And we're going to restore the registers from the new context and switch over to that new process. So this is context switch from old to new. And we can see that this is some assembly to actually do that. Now, to understand what is really happening there, it's very hard to do it just from the code. So let's actually look at a diagram for it, all right? So let's start from something that we're more familiar with. Let's start from a system call, okay? Actually, there is one more thing that I want to look at in xv6. So I said this context and trap frame. These are the register context for this process. That's true, but it's actually two different forms of register context. This trap frame actually points to the location of the user level registers for this process. So when a system call is made, remember that what we need to do is effectively the system call instruction is made. We let the hardware switch the processor to mode 0, and it starts executing at a stack pointer and instruction pointer pre-configured by the operating system, right? The first thing that it will also in some way save the stack pointer, right? At that point, we execute some code that I'm not going into here to actually save all of the user level registers onto that stack, onto the user level, onto the kernel level stack. And TF, the trap frame, which we saw here in the code, is then within that process structure just set to point to where we saved all of those registers. So we just saved all of the user level registers onto the stack, as we've talked about for a system call many times, and all that we've done now is set that TF pointer to point to all of those registers. So now we can actually refer to all of those registers through a trap frame and not necessarily through something else. And if we look at a trap frame, we see that it effectively includes a variable for each of the registers on the system, right? AX, BX, etc., etc. I'm not going to go into the details of that. Okay, so we've saved all the user level registers onto the stack, and we've started executing a system call handler, in this case for system call N, right? And imagine that we're executing that system call handler, and you can see that the stack pointer in the system points to effectively the top of the invocation frame for that system call, right? Okay. So then as part of that system call, imagine that we are executing some code where we want to wait for I.O., right? Wait for I.O., not necessarily a call within xv6. It's just kind of an abstraction for saying, well, there's a function that the system call handler called wait for I.O. that decides that it wants to essentially block, right? So at that point, we might add ourselves onto a device queue, that whole shebang. But what we do next is effectively we say, well, I no longer want to execute. I want to essentially block, put myself into that waiting state, or into, a blocked state. Oops. I accidentally hit a very bad button there. I apologize. Oh, the fun. And because it no longer wants to execute, it effectively calls the scheduler. It says, hey, scheduler, you execute, and I no longer want to execute, so you call somebody else to execute, right? Okay, so now we've added an invocation frame for the scheduler onto the kernel stack. Fine. Now, the scheduler has its own decision about how it wants to actually switch to the next thread, but eventually it wants to call this switch function, right? So the switch function, I've included kind of the what's effectively the C prototype below, and the code that the scheduler would call up top. And effectively what it's doing is it's saying, I want to call schedule with a pointer to the current processes. The current process is proc0. I want to call switch saying that the current process is proc0, and here is its context. Context is going to be the field within this structure that points to the register state within the kernel for this process. And then it says, I would like to switch to the next process, here kind of referred to as new, and here's the register state for that next process that I want to switch to. So this is effectively how the scheduler is going to call the switch function within the kernel. Now we saw that the switch function is assembly, but it behaves like a function itself and adheres to the cdecal calling conventions that we talked about, so it can be invoked as per a normal function. Now, when we call a switch function, we know that the compiler is going to do a number of things that it always does when we just call a function. Oh, sorry, I skipped this. we have the current process and we have the next process that we want to run to. So this is just a diagram showing that we're kind of pointing to their different contexts and passing lows into switch, right? Now, in that next process that we want to switch to, it also has state within the kernel. So it might have its own stack within the kernel. Perhaps it's also executing a system call, which means it had some user-level registers that were saved when we switched down to the kernel. It executed syscall ems handler, then called a function foo, then called a function called yield, which essentially says I don't want to run anymore, which might have called the scheduler, right? Now, what's interesting here is that you'll see where this comes from, but the context within that process that we're trying to switch to actually points to the top of the stack. So this is a hint as to what we're about to do within the current process, within process 0. But what I'm pointing out here is that we have this process that we want to context switch into that we're calling next, process 1. And the context variable within its struct proc is pointing to the top of its stack. And I told you context is where the registers are, so it seems like the registers are somewhere on the stack. Okay, so let's get back to the point where we're in process 0, the current process. We're in the scheduler. The scheduler wants to call switch and say switch out of the current process into the next process. All right. What does that look like? Okay, when we invoke switch, it's going to push the 2 arguments for switch onto the stack, because that's what the compiler always does when we call a function, as we know. So it's going to push the pointer to context onto the stack. It's going to pass the pointer to the current context onto the stack after that. This is a pointer to this pointer. This is just the wherever context points. And then, of course, whenever we call a function in C, it's going to push the return address to return to within the scheduler code onto the stack at that point. So now we are executing in switch, right? We have set up the invocation frame. We're starting to execute within the switch function. You can see the stack pointers pointing to it. So this is what switch looks like. I've just cleaned it up a little bit from what I showed you in the code. And you can see now that first thing that we're going to do is just actually save the 2 arguments, the pointer to the context pointer, into what I'm calling here the current register. Note, there is no current register. There is no name for a register called cur. So I'm just doing that to simplify understanding of this code. And then it's passing the variable that's offset 8 from the stack pointer, i.e. the next context, a pointer to this address, into next. So now we know that current is pointing to this pointer, and next is pointing down here on the stack. Now, what switch does is it breaks its execution into 3 different phases. So this first phase, what it does is push all of the registers that need to be saved onto the stack. So if we look at what this first stage is doing, all that it's doing is pushing EBP, then EBX, then ESI, then EDI onto the stack. So it's literally just saving all of the registers onto the stack. And you can see as we push onto the stack, that is updating the stack pointer as well, right? So that's the first phase. Save all of the registers. Okay, so now we know where the register saving happens. It's actually just this. Second, what we're going to do is first save the stack pointer into this variable right here, context within our proc zeros, the current process's structure. So now we're setting this context to point to the top of our stack. So we know that context always points effectively till the current registers for the process, for this process, for proc0, right? Second, it's going to move next into ESP. So that's going to change ESP from what it was here to point to the stack for the new process, the next process that we want to be executing. So we know that context always points to the top of the stack until the registers that were saved. So now all that we're doing is switching stacks from process 0, from the current, into process 1 stack for the next. So we've effectively switched stacks, which is pretty cool. And then all that we do is pop all of the registers and return. So what happens? We have all of the registers that we had previously saved onto this process when we switched away from it, much like we did over here for process 0. And we have all of the invocation frame stuff for invoking switch here. And after we pop, we get rid of all of the purple. After we ret, we effectively get rid of all of the teal. And we resume execution in the scheduler where it was executing for process 1 when it was actually going through all of these invocations. So at that point, schedule will probably return to yield, which will probably return to foo, which will then resume computation for this process. At that point, it might even just keep returning and keep returning until it just switches back to user level, right? So this is effectively a context switch. There's one small little thing here that's weird that I've emphasized with red. We actually have a pointer on the stack to the next thread here, and that really doesn't point to a valid address anymore. And actually the context right now doesn't point to a valid address either. So context actually is only valid when the thread is not in a running state. When a thread is running, there's nothing for context to really track because the current registers of the CPU hold the registers for this process by definition of it being running. Only when we move it to the ready state, the runnable state, or the waiting state will we actually go through the process of saving all of its registers onto the stack and setting context appropriately. So I just want to review here. Pre-calling switch, process 0's stack is active, but it wants to be switched away from, right? We want to save all of its registers. And process 1 has been determined by the scheduler to run next. After switch is called, process 0's stack and context are prepared to be switched back to at some point in the future, which is to say that we've saved all of the registers for it onto the stack, and we've set its context to point to the valid address that contains all of those registers so that we can switch back to it in the future. And process 1 stack is active and its registers are restored, so it's executing. So this is effectively a context switch in xv6. What I want you to kind of walk away from all of that, I want to back up again because that's a lot of detail. I want to back up again to kind of a summary of where we're at. Processes, again, we need to implement them using schedulers, different states, traversing them through queues in the system. But at the highest level, remember they're a computation. They're an abstraction for computation and memory. They're really implemented without magic. Hopefully everything that I just went through shows you that one of the most magic parts of a process's lifecycle, i.e. the context switch to and from them, is nothing magical. It's just structures, C, and assembly. That's it. And not even that much assembly. We really looked at one of the 2 places of assembly that we'll see in this class. So next class, we will continue to talk about these type of issues, and we will focus on the APIs provided to user level to manipulate and use processes and provide communication between them. Thank you very much. Hope you're doing all right.